Good day. You are welcome back to another chemistry class. Last week we discussed on atomic structure, and before we left I gave you an assignment to do. Now let's take a look at the solution to last week's assignment. This is the solution to last week's assignment. The writings in red are the answers to the blank spaces you are asked to fill in. Let's go through it, and if there's any correction, take note of the correction. In today's lesson, we'll be treating the topic isotopy. Okay? And under that isotopy, we'll be concentrating on isotopes. But before we continue, let's take a look at the definition of isotopy and isotopes. Isotopy, this is a phenomenon whereby atoms of the same element exhibit different mass number but have the same atomic number. Isotopes are atoms of the same element with the same atomic number but different mass number. Okay, from our definition, we did say that isotopy is a phenomenon whereby an element has two or more atoms that have the same atomic number but different mass number. Okay, and that is what isotopy is. But we say the isotopes themselves, they are atoms of the same element having the same atomic number but different mass number. I want to caution here from marking of external exams. I've seen that students make some particular mistakes in their definition of isotopes. They define isotopes as elements having the same atomic number, and that is very wrong because no two elements can have the same atomic number. Last week when we were talking about atomic structure, I did tell you that the identity, the specific identity that element has, what makes that element is its atomic number. So no two elements can have the same atomic number. So you don't define isotopes as elements having the same atomic number. But isotopes are atoms of the same element having the same atomic number but different mass number. Example of elements that exhibit isotopy are hydrogen. Okay, we have hydrogen, we have chlorine, we have oxygen, we have copper, carbon, and the rest of them. When we take hydrogen, for example, hydrogen has three isotopes. The first one, we call it protium. It has atomic number 1, mass number 1. The second isotope of hydrogen is deuterium. It still has atomic number 1, but mass number 2. Then the third one is tritium, with atomic number 1 and mass number 3. All these are atoms of the same element. Why are they atoms of the same element? Because they have the same atomic number. Once you see any element with atomic number 1, it is hydrogen, no matter its mass. The atomic number tells you what the element is. So hydrogen has 3 isotopes. Then chlorine. Chlorine has 2 isotopes. We have chlorine, atomic number 17, mass number 35. And then we have chlorine with mass number 37 and atomic number 17. These are 2 isotopes of chlorine. Once again, you see that they have the same atomic number, but their masses are different. That tells you that they are atoms of the same element. Then oxygen. We have oxygen with atomic number 8, mass number 32. Okay? Now 16. Sorry. Then we have another isotope of oxygen with atomic number 8, mass number 17, We have another isotope of oxygen with atomic number 8 and mass number 18. All these are isotopes of the same element. Why? I mean, they are atoms of the same element because they have the same atomic number. Okay? Then, carbon, let's take a look at carbon. Carbon will have carbon 12 and atomic number 6, which is the common one that we know. When we say what the atomic number of carbon, we know is 6, mass number is 12. But it has other isotopes apart from this carbon 12. We have carbon 13, okay, with mass number 13, and then you have carbon 14. This carbon 14 is isotope, which is used in carbon dating. If you have treated carbon dating, you know that carbon 14 is what is used for carbon dating. So these one are all isotopes of the same element. So these are some examples of elements that exhibit isotopy. Now, take a look at these elements and all these isotopes. If I ask you, what is responsible for the difference in their mass numbers? What will you say from last week's lesson? If you look at them now, what will you say is causing the differences in their mass number? Did I hear you say the difference in the number of neutrons? You are correct. Because last week we said that mass number is the sum of protons and neutrons in the nucleus of an atom. And since atomic number is the number of protons, and mass number is protons plus neutrons, and if this one has atomic number 1, what does that tell you? This one does not even contain a neutron. Because 1 plus 0 will give you 1. Even if there is 1 neutron, that would have made this one 2. But the second one, you have atomic number 1, that means there is 1 proton, and the mass number is 2. That means the number of neutrons, the neutron is only 1. That is why when you ask the proton and neutron, you have 2. What about this one? How many neutrons do you think this hydrogen isotope has? Yes, you are correct, 2. Because the atomic number is 1, which is the number of protons, and since the mass number is 3, if you subtract 1 from 3, you'll be left with 2. That means the number of neutrons are 2. And that's the same thing you would do here. If you are asked how many neutrons are in this isotope, all you need to do is to subtract the atomic number, which is the number of protons, from the mass number. Your answer will be the number of neutrons. In this case, if you do it correctly, you find out that this one has 18 as its number of neutrons. And if you do the same thing here, you find that this one has 20. So what is responsible for the differences in their mass number is the number of neutrons. Now, another thing I want to take a look at is that these elements that exhibit isotopy, their mass number are not as straightforward as we saw last week. Because last week we said mass number is just the addition of number of protons and neutrons. But look at this one, we say like hydrogen, it has 3 isotopes. So which one do we take? Do we take this one to say hydrogen has atomic number 1, mass number 1? Or take this one and say hydrogen has atomic number 1, mass number 1? No. For elements that exhibit isotopy, the relative atomic mass is the average of the masses of the different isotopes. That's what gives you the relative atomic mass of those elements. So you will need to take the average of the masses of the different isotopes. That will give you the relative atomic mass. Now let's take a look at some examples on calculation on isotopes to press forward this issue. Okay, in the question we have as our example 1, the question says that chlorine has 2 isotopes. One is has 75% of chlorine 35, atomic number 17, and you have 25% of chlorine 37, atomic number 17. And the question says we should calculate the relative atomic mass of chlorine. Okay? Now look at the percentage. This is 75%. What does that tell you from your knowledge of percentage? is 75 out of 100 because this percentage means 100. So this is 75 out of 100 of the mass 35. Then this is 25 out of 100 of the mass 37. Okay? To do that, you have to calculate what this mass is and add it to this mass. Okay? Divide all by 100, that will give you the average mass. So how do we go about it? This one, the percentage, 75% means 75 over 100. Multiply it by the mass, which is 35. Okay, whatever answer you have here, you add it to this one. 25% means 25 over 100 times the mass, which is 37. Okay, if you did this calculation correctly, this one should give you 26.25. Okay, plus this one, if you do this multiplication correctly, it should give you 9.25. Okay, that's to say you divide 75 by 100, which will give you 0.75. Then you multiply by 35. That will give you this answer. 25 divided by 100 will give you 0.25. Then you multiply by 37. That will give you 9.25. If you add the two masses together, that will give you 35.5, which is the relative atomic mass of chlorine. You can see that it is neither 35 nor 37 because you have now calculated the average of the two masses. Can you now see the reason why the relative atomic masses of some of the elements are not whole number? So next time when you see such questions, why are the relative atomic masses of some elements not whole number? The simple reason is because of the existence of isotopes. Once the element has isotopes, it's very likely that its relative atomic mass will not be a whole number because it is an average of the different isotopes. Okay, that's all about question number 1. Let's take a look at the second question.
Example 2. An element X has two isotopes, X20 and X with mass 22, in the ratio 1 to 3. What is the relative atomic mass of X?
Now, in question 2, you will notice that in the first question, they gave us the relative abundance of the different isotopes in percentage. But this one, they gave us ratio. They say they are present in the ratio 1 to 3. Say you have the two elements. One, the mass is 20, and the other one, the mass is 22. Okay? The one with mass 20, they say is present in the ratio 1. The one with 22 is present in the ratio 3. Now, just as we did with percentage, we had, the first question we had 75% and 25%. We added these two and it gave us 100%. Okay? So, the same thing you do here. You add the ratio, 1 plus 3, that will give you 4. That means the total of the ratio is 4. Just like you had the total of the percentage is 100. So, you just follow the same step that we did in solving the first question, you will arrive at it. So now, the initial, instead of saying percentage, now you have 1. Just 1 over the total ratio, which is 4, times the mass that has this ratio 1, which is 20. Okay? Whatever answer you have here, you add it to the other one. The second one they say is in the ratio 3. Okay? And the total is 4. Divided by 4 times the mass of that isotope that has the ratio 3, which is 22. Okay? Whatever answer you have in these two, you multiply it. If you do this, division 1 divided by 4, it will give you 0.25. And by the time you multiply by 20, that will give you 5. Okay? Plus this. If you divide this 3 divided by 4, that will give you 0.75. You multiply it by 22, that will give you 16.5. Then you add the two masses together, that will give you what? 21.5. And that is your final answer. Can you see that there's really nothing difficult in the calculation of isotope. In just 1, 2, 3 steps, we have already arrived at that. Okay? I can see some of you getting excited that this thing is simple. Okay, and that is where we want to stop for today. Before we go for today, let's take a look at our assignment. Please, I beg of you, last week's assignment, many of you didn't submit the assignment. That is, if you did it, I didn't see it. I thank all of you who submitted the assignment. Please, for this week's work, I want to encourage all of us to solve it and then upload it to my WhatsApp page or my email.
The first question says, the relative atomic mass of an element is 21.5. The two isotopes of the elements are Z with mass 20, occurring in nature 25%, and Z with mass M, occurring 75% in nature. Calculate the value of M. Second question. An element X with atomic number 29 has two isotopes, Y and Z. Isotopes Y and Z have 34 and 38 neutrons, respectively. Calculate A, mass number of each isotope. B, percentage abundance of each isotope if the relative atomic mass of element X is 63.5.